All right, so yesterday, the day before, we talked about measuring segments. Now we're talking about measuring angles. And once we conclude this, it's going to have we're going to have all the necessary tools to build the rest of geometry. Okay. With distances and angle measurements, you can build all your other two-dimensional, three-dimensional shapes. Okay. This section parallels a lot with section 1.3. If you think about 1.3, we had the ruler postulate, which allowed us to measure distances. Here we have the protractor postulate, which is the device that we use to measure angles, right? In 1.3, we had the segment addition postulate, allowed us to add segments together. Here we have the angle addition postulate, allows us to add angles together. Okay, so there's a very similar kind of contrast between the things they're going to occur in this chapter or this section compared to the last one. Just vocabulary-wise, there's some things to talk about. An angle, first, is a figure formed by two rays that share the same endpoint. Two rays that share the same endpoint. That endpoint that they share or that is in common. Okay, so a lot of times instead of saying the word share in mathematics, we use the word common. So their common endpoint is called the vertex. And the rays we usually refer to as just the sides of the angle. Okay. So just a quick visual. I think everybody knows what an angle looks like, but by that definition, we're looking for a point. That's going to be my vertex as I set this up. There's one ray. Okay. Now, that would be the second ray. Does that make sense? They share vertex A. We would have ray AB as one side of my angle and ray AC as my other side. Is that doable? Okay. All right, so we've got some symbolism, some ways that we're going to refer to angles, describe them, name them, that kind of thing. And this can get messy. There's good ways of doing this. There's bad ways. All of them are acceptable in certain situations, and some of them are unacceptable in certain situations. So, says you can name an angle by its vertex. Okay, so I'm going to name this angle here because its vertex is letter A. I can call it. I'll just put these in these boxes down here. Angle. So we use this little symbol out front. That is an angle. Instead of writing the word angle, we use that little symbol out front and then say A. Okay. Sometimes you will see that little symbol being used like that. Sometimes people draw it this way. Sometimes people are more like a greater than sign, and then sometimes they put the little arc in there as well. But those are kind of the three general ways that you're going to see them talk about an angle and describe it out front. So that's one way. Okay. Another way is there will be times where they put a number inside that does not have a degree symbol on it. So if I put a degree symbol on it, if I put that there, now I'm giving you a characteristic about the angle, and I'm not giving you a way to name it. Okay. They usually do this if there are multiple angles in the picture, so you can easily reference them, easily talk about them. So we can call this angle 3. Okay. The best, safest, most appropriate way is to name it with 3 letters. Okay. When you name it with 3 letters, those would be my 3 spots. The middle letter always has to be the vertex. Okay. And then the other 2 spots need to be points that are on the rays. Okay. So I need a point that is on that top ray, and I need a point that is on the bottom ray. So those 2 points that they identify for us are B and C, right? So B and C. The way I judge this or think about this is if I want a set of directions to start tracing out this angle, if I start at B, which is the first letter in my name, and I go down to the second letter in my name, and then finish at the third letter in my name, did I trace out the angle? Okay. Now, what if I did this? What if I started at C, went to A, and then went to B? Does that trace out the same angle? Start at C, go to A, finish back up at B. Is that the same angle? Okay. So you can name it either. The order does not matter as long as A is in the middle. Okay. Now, in addition to that, what if I put like point W on here, and I named it angle WAC? Same angle. Okay. And those are little things that we might have to pay attention to as I name something. Depending on the points that they give us, I might name it a little bit differently than you. But if both of our names allow us to trace out the same image, then we're talking about the same thing. Is that okay? Okay. So there are times that structure of naming angles is inappropriate. Some of them are inappropriate. So let's say I've got something like this, and I call this angle 1, and I call that angle 2. And you can talk about those angles. And if I say everybody look at angle 1, I think everybody knows we're going to look at this one, right? Okay. If I say look at angle 2, you know what to look at. So I'm going to just talk about these, color them a little bit. So if I say look at angle 1, everybody knows look at the blue one. If I look at angle 2, everybody knows look at the green one. But if I ask everybody to look at the purple angle, because that's an angle up there, right? Okay. Do I call that purple angle 1 or 2, or what do I call it? That's a problem, isn't it? So I can only identify individual angles that are not being added together or combined to make a larger angle with numbers like that. Okay. So what I need to be able to do is have some letters on here. So if I say, let's put B here, let's put A there, let's put C there. Now if I wanted everybody to talk about that bigger angle, and that's kind of how I'm going to draw your attention to that bigger angle, is draw an arc through it. Okay, so start at one spot of that arc and travel all the way through. So where I'm talking about the sum of 1 and 2 now. So I would call that angle BAC. Does that make sense? Okay. Now here's where if I just say angle A, everybody look at angle A. Well, A is right here, right? That's the vertex. So some of you might be looking at angle 1, right? Does that make sense? Because that's got vertex A. Some of you would be looking at angle 2 because that's got a vertex A. And then some of you might be looking at, I don't like this purple color, but you'd be looking at that angle because it has vertex A, right? So we have 3 groups of people looking at potentially 3 different angles. And that's a problem if we're going to try to talk about some procedures in the way we do things. So if I wanted you to talk about those specific angles in different ways, I would probably maybe need another point on here. And now I say, especially if I'm not using the 1 and the 2, now I'd say everybody look at angle BAF, and we're all on the same page. If I say everybody look at angle CAF, we're all on the same page. Does that make sense? Okay. And that's the thing with naming shapes. There's going to be, times when those shapes are standalone all by themselves like this, and you've got some leeway on how you name them. Sometimes they're being attached to one another, and then you have to abide by some certain procedure. Okay. We like to talk when we take an angle, and this makes a little bit more sense visually in something like this. Okay, so those rays go on forever in all directions, or the directions that they're set up, right? Does that make sense? Okay, so my yellow graph here, my yellow grid, is a 2-dimensional plane. Okay, when I draw my angle up there, it divides my angle into, or my plane, sorry, divides my plane into 3 different regions. There's a region that is on the inside of my angle. Okay, would you guys agree that? Let's see here. Like this stuff here would be on the inside of my angle, and that goes on forever. So a word for inside that we use, instead of saying inside, is interior. That's a terrible color. Okay, so we've got our interior. Everything that would be on the outside would be called the exterior. Okay, so all of this stuff would be exterior. Okay, but I told you it breaks the plane up into 3 regions. Look at point A right there, which is the vertex of the angle. Is that on the interior? Is it on the exterior? No, it's on the border, right? Think about like if you had a brick wall between your property and your neighbor's property at home, and you were standing on top of that brick wall. Whose yard am I in? Yeah, I'm really not in either, right? I could either argue I'm in both or I'm in neither. If I'm standing on the line of Ohio and Indiana, standing on the line, who claims me? Does Ohio claim me or does Indiana claim me? Okay. Same thing you do with counties. So if we have a point that is on the angle, then we say it's on the angle, but it's not part of the interior or part of the exterior. So those are the 3 regions that we're going to talk about. There's going to be a lot of statements and rules later on that say points on the, and I think we see one today, with points on the interior of an angle we can do whatever with, or points on the exterior of this angle, or there's a point on the exterior of this angle, and that should allow us then to kind of visualize where it should exist. So we're going to see those words a lot in this class, not just for angles, but other shapes as well. Questions on anything so far? It's all right. Let's hide this. All right, so we measure angles, okay? There are 2 things that we use to measure angles, 2 units that we use to measure angles. And the one that you guys know the most about and that we're going to focus on in this class are degrees, okay? And we're going to focus on angles that measure right now between 0 and 180 degrees, okay? As the class progresses, we'll start talking about angles that are bigger than 180, and as you start taking maybe my trig class, we'll talk about angles that are negative, which you might think, well, how can an angle of measurement be negative? But it's possible, okay? There's another unit, and they're called radians, okay? So what a degree is taking my circle, okay, and basically chunking my circle into 360 slices of pie or pizza or whatever, right? That makes sense? And each one of those slices is then a degree, okay? Now that's something that like we have, like people always ask, well, why is 360 degrees? Why that number? Okay, why not use a number like 300? That's a little bit easier to deal with. Why not 400? Okay, the reason for that, I'll give you a little bit of history here. A long time ago, Babylonians. You guys know who the Babylonians were? Ever heard of the Babylonians? Okay. So what they figured out, so if they had a, let's say, hexagon, where's it at? There we go. So they had a hexagon, okay? And they knew, based off a measurement, that they could take a hexagon and create those 6 triangles. And what they were able to do is realize that with those 6 triangles, we are going to, every time we draw a hexagon, if I look at E to D, D to G, G to E, all those segments are equal. So we came up with what we call an equilateral triangle inside there. You guys have heard that word before, right? Okay. An equilateral triangle is also an equal angular triangle, and they knew this. They knew they could measure this, and they found out that that angle right there, see if I can ask you for the angle. Oh, that sucked. The angle tool in this program is a pain in the butt. But we see that angle there is 60 degrees. This angle up here, if I did the same thing, it would be 60 degrees, and that would be 60 degrees. Does that make sense? So they knew that this was 60. Well, what's 60? If that angle right there is 60 where my cursor is, that's 60, that's 60, because all these triangles are the same. That's 60, and that's 60. What do those all add up to? 360. And you might be saying, okay, well, 360, great, that does give me the circle, but where's the circle out here? Well, they knew that the hexagon allows us to draw a circle using the center of the hexagon. We can draw a circle that passes through all 6 of those points. And now, if we could add all these up and get 360, then when I take the hexagon out of there, when we remove that polygon, we should still have 360 degrees there. Does that make sense? Okay, so that's where the idea of 360 comes from.
Pardon the interruption. Staff, please check your emails regarding a survey in Schoology that needs to be completed by the end of today. And staff members, please check your email regarding a survey in Schoology that needs to be completed by the end of today. Thank you.
So degrees, we're accustomed to those. Those are things that you are used to. So much like, and you guys talking about things that you do maybe in a chemistry class. What units of measurement, what system of measurement do you use the most in science classes? Do you use feet and inches and miles and stuff? You use the metric system, right? Okay. We are one of 3 countries in the world that do not use the metric system. Okay. We use the U.S. customary system. Okay. So we're used to like pounds and feet and inches and that kind of stuff, right? And the U.S. customary system is kind of a pain in the butt because it's not based off of a constant power of 10 like the metric system is. Okay, but if I were to ask you to measure the distance between here and Walpock, you guys would understand that if I gave it to you as miles, right? You're going to be comfortable with that, okay? Or if I ask you if you're going to travel 60 miles per hour, you've experienced that. You understand how fast 60 miles per hour is. But if I ask you, give me an experience where you've driven 34 kilometers per hour, do you really know how fast that is? You're not used to kilometers, right? Okay, kilometers, it takes a little bit more than 1 kilometer, about 1.6 kilometers to make a mile, right? If I say from distance from here to Walpock is, 20 some odd miles, but in kilometers, maybe it's 35 kilometers, we can't really judge that. We're not used to it. We don't use that in our everyday operations. So you guys are more accustomed to miles as a unit for measuring distance than you are kilometers, much like you are more accustomed to degrees than what you are to radians measuring angles. Does that make sense? So I'll show you what a radian is. We're not going to use it a whole lot in this class, but there has been times in the past in like a homework assignment, they'll mention the word radian. There's been, and of course, exam questions that use the word radian. If you ever use your calculator, which we will quite a bit in this class with angles, there's a radian button. So there's some things that we have to pay attention to there with that stuff. So I'm going to, all right, so this applet kind of shows us the idea of what a radian is. So they take out, the structure of it is that they measure out this distance here. What's that distance right there called? A radius, okay? And that maybe identifies why we call it a radian. But we do that. And now what they're going to do is they're going to take that radius and they're going to slide it outside the circle. But now that distance right there, even though it's moved and rotated, that is still the same length as that. Does that make sense? Okay. Now I can take like a piece of string that is a foot long, and I can bend it and make it all curvy and however I want to. It's still a foot of string. Does that make sense? So that radius, that distance, is still a radius, and it's still the same exact distance when I bend it around the circle. Does that make sense? Okay. Now what I'm going to do, if we look at that, we've got two red points, and we've got our center of our circle. And that creates an angle. Does that make sense when we do that? That angle right there is called a radian. Okay. Now, the nice thing about radians, a radian is approximately, I think it's like 56 degrees or something like that, somewhere around it. It's not it doesn't work out to be a really nice approximation, but we can do this. So that's 1 radian. There's 2 radians. Okay. There's 3 radians, and we need a little sliver more to get to 180 degrees. Does that make sense? Okay. Well, we had 3 radians, and that little sliver more works out to be exactly the decimal point for us getting to pi. Okay. So 180 degrees is equal to what we call pi radians, which is like saying right there, that's like saying 1 mile is equal to 1.6 kilometers. Okay, that's a conversion factor. And then if I go pi radian and go all the way around, I get 2 pi radians as going all the way around. And that, the trig, we'll talk about that and how that works with the formula 2 pi r, which is the circumference of a circle, correct? Okay. And there's the 2 pi part that is involved there. But radians, for the most part, we're not going to deal with them directly, but you might see those words pop up every once in a while. I just need you to know that it's another unit for measuring angles. Okay, but we're going to concentrate on degrees for the most part. All right, so these are things, guys. These are things that I'm going to kind of breeze over. These should be things that you guys have known from the past. We've got acute angles. There's 0 to 90. We've got right angles being 90 degrees, obtuse, anything bigger than 90 but less than 180. Okay, so everything we do, we're going to go from 0 to 180. We will talk later on, like I said, like a 270 degree angle. A 270 degree angle is still obtuse, but there's different ways that we're going to approach that angle. A straight angle is 180 degrees. So a straight angle is also what's a straight angle create? A line, which we've also talked about as being opposite rays, correct? Okay, so now we have really 3 different ways of identifying the same object, the same shape. And as we work through the course, sometimes they'll say in another vocab word that we created a straight angle. Sometimes they'll say we created a line. Sometimes it says they're opposite rays. We just need to make sure that we can tie those together and make them the same. Is that all right? Okay, that's stuff that hopefully we maybe knew already. Okay. All right, so this is the protractor posture. So the protractor posture, I think it might make more sense, guys, if I can demonstrate what it is instead of maybe reading it through with you directly. So, all right, so you guys, so if I've got this angle here, and I want to measure that angle, you guys are probably most familiar by taking a protractor and placing that protractor, if I can get it to move, right there. You put that little hole that's on the protractor, you put it on the vertex of the angle, right? Okay. And then a lot of us would like rotate that so that one of the rays is lined up with the 0 marking on our protractor, right? And if it's going through 0, then all I've got to do is come up here and say, okay, going through 0, going this direction, I hit 90, and then there's like 3 more after that, so maybe 93 degrees. Does that make sense? Okay? But you don't need to do it that way. What the protractor postulate says is that we are going to take, we're going to take a straight ray. Let me do it this way. Let me kind of demonstrate this to the side real quick. We're going to take a situation like this, where we've got a set of opposite rays. And if let me color one of these, or both of these rays, so we can talk about them a little bit easier. Ray. All right, so they're going to say, we're going to take this blue ray, and we're going to take this red ray. And we're going to pair the red ray with the number 0. And we're going to pair the blue ray with the number 180. Does that make sense? And then what we're going to do is we're going to create another ray. And let's see if I can do this maybe a little bit easier for you guys to see. We can do it that way, that's fine. So we're going to create this other ray here. And basically what we're going to do is that every time that I stop that ray, we're going to pair it with a number between 0 and 180. So maybe that's like 1. That's 2. That's 3. That's 4. That's 5. That's 6. And as I work all the way around, okay, we can maybe see that, let's see here, segment with given length. That won't work. What I want to do is trace this so that you can see kind of an image here. Let's see if it'll work. What we're going to try to do is create, as I move this around, I create kind of a semicircle, right? What's that shape kind of collectively look like? Does it kind of look like that? Does it look like a protractor? Okay. So what we're saying is that every time that we move one of those rays above that line and we pair it with a number between 0 and 180, we generate or we create this protractor. Okay. And then if I want to measure anything on my protractor, any angle, I don't have to set it up like we had this ray going through 0 and that ray going through 93. We can simply capture the two values. Now we have to be on the same row. Okay, so there's 2 rows of numbers, right? There's a top row and a bottom row. We have to be on the same row, but I can capture that number right there, okay, which was like 134 if I'm looking at the top, okay? And then I capture that number right there, which is 41. What do you think I can do with those numbers to get that number? Subtract them. Is that not the same exact thing that we did with the segment postulate? Or the ruler postulate, when we're not adding, but trying to find the lengths of something, okay? You took the coordinates, so these are just generating coordinates for our arrays, and we subtract those coordinates to find the angle between them, okay? So back to these notes here, and this image I'm showing you, the ruler postulate and the protractor postulate are expressed very similarly, okay? If I want to find the measure of an angle, in this case, they're finding the measure of angle COD, okay? Where C, lowercase c, is the coordinate for the red ray, and lowercase d is the coordinate for the blue ray. All we have to do is take the absolute value of C minus D, and that's going to give you the measure of that angle every single time. Okay. Now, if you don't take the absolute value, you might get a negative number, and angles to us right now have to be positive values. And even when you get into trigonometry, when you talk about negative angles, they're still going to look like that. it just talks about the direction that the angle swept out, okay? So if I look at my clock right now, our clock, when the minute hand moves around clockwise, okay, that is actually in mathematics opening up what we call a negative angle, just because of the direction that the ray moves from its starting point. If it was going the other way, then it would be considered a positive angle. But we're going to always talk about positive angles in this class, so we take the absolute value. Is that okay with everybody? So on your test or quiz, what I will do is I will create a protractor that has like a bunch of different rays kind of sticking off of it, and I will label each letter, and I'll say, okay, look at ray or angle COB or something like that. Trace it out, find the measurements that those rays are passing through, just subtract them, and that's going to give you your angle. Does that make sense? I'm not going to give you a protractor to manipulate. I want you to use this idea, so it'll be a static picture already set up for you, and you're just going to draw your conclusions from that. Is that all right? Okay. So I got one more concept I want to talk about. Congruent angles are just angles that have the same degree, okay? They have to be same shape, same size. So same size means the degree, and obviously, if I'm looking at two angles, they are both the same shape. That gets us to this last concept of the angle addition postulate. This is exactly the same thing, same concept as the segment addition postulate. We're going to add smaller angles together to get an overall total, okay? So here it says, if point B is on the interior of angle AOC, then the measure of angle AOB plus the measure of angle BOC is equal to the measure of angle AOC. So if we look at the angles that they're given there, the colored yellow angle plus the blue angle should end up giving me that total angle, okay, the overall. Is it okay? The one thing that we have to pay attention, and this is why we talk about this vocabulary word, that's a key phrase, key word or term in this. Because if B is not on the interior of angle AOC, let's say here's A, here's O, and here's C, but I put B out here, would you guys agree that AOB, which would be that angle, plus angle angle BOC, which would be that angle. So I'm taking that little small angle, this whole angle. If I added those together, would it give me that purple angle AOC? Does that make sense? So that's why that word interior is critical, because if B is just anywhere, this relationship here, this conclusion does not exist. Okay, we have to know where it's located. So when we look at a picture like this, okay, if I look at my structure, and I think I like to use, especially early on, okay, and I get a lot of people do this. This is something, guys, that is going to, angle addition is something that almost shows up in every single chapter as we move on through the year. So I get a lot of people that like to color their angles and say, okay, I'm going to take the blue angle and the yellow angle, and those are the ones that are going to be added together, okay? So they'll write down the measure of angle R, it's a Q, so RQS plus the measure of angle SQT should equal, what would be the overall angle? Measure of angle RQT. Now, I didn't necessarily speak of this, but when I want to talk about the measure of an angle, if I just say angle RQS, then I'm talking about the shape. If I put that little lowercase m out in front, that means I'm talking about its measurement, its degree. Does that make sense? Okay. So that's kind of comparable to if I'm talking about a segment, and I want to talk about the shape, I put the bar over the top, right? If I want to talk about the segment's distance, I delete that bar. So now, this number, or this expression here, 4x minus 20, that is what RQS is. That's its degree. Okay, now it's unknown, it's arbitrary, it's a expression, but I can replace RQS's measurement with 4x minus 20. I can look at SQT. Okay, its measurement is going to be 3x plus 14. So that plus sign needs to stay, and then I go 3x plus 14. And now I need RQT's measurement. So I need the measurement of that thing right there. So that measurement should show up somewhere, either in the picture, but usually because it's hard, just because the picture, like if I put I think it's 155. If I put 155 right there, it's hard to tell what that 155 is being supposed to represent. Does that make sense? So they'll give that third measurement over here in direction somewhere. So measure of angle RQT is 155. Now, is that an algebraic equation that we can solve? All right, so we combine like terms. So 4x and 3x gives me, good, so 7x minus 6, negative 20 and positive 14, equals 155. So that's going to give me 61? How many times does 7 go into 16? 2? And how many would you have left over then? You have 2 left over, right, out of the 16? So then you'd have 21 left over as a final amount. So how many times does 7 go into 21 then? 3. So x equals 23. Now, just like we talked about yesterday and the day before with segments, x can be anything. X can be 0, it can be negative, it can be positive, it can be fractions. What you need to make sure you are convinced of is that when you plug it back in, the angles that they represent have to be positive. So when I go 4 times 23, what's 4 times 23? Okay, 92. Okay, so quick way of doing that, what's 4 times 20? 80. And then what's 4 times 3? 12. 80 plus 12 is 92. Minus then the 20 that's there, so 72 is that angle, right? 3 times 23. 69 plus 14. 83, right? Okay. So what's 83 plus 72? 155. And that's your kind of built-in check, right? Okay. So that's what the question asks for these two angle measurements. So you might go, you're going to get them anyways. You're going to get the 72 and the 83 anyways. Go one more step to guarantee it they're right, and add them together and see if you get that 155. Why don't you guys take a minute and see on your own what you come up with on this next one. All right, so I'm looking at, like, when I go ahead and try to determine what angles I'm going to be adding together, I'm going to say the measure of angle, UTH plus the measure of angle HTS is equal to the measure of angle UTS. You guys agree with that? So that angle there plus that one there should give me the overall UTS. So once I can figure that out, that's the geometry of things, okay? And that's something that I'll talk about all year long. Once we figure out the geometry shouldn't be that hard, okay? And then that's all year long. But it's the algebra that's hard, okay? And I make the analogy all the time. You guys know what slope is? You guys know what area is? Just start your calculus. That's all calculus is, talking about slopes and areas. But in order to investigate it and analyze it and actually apply it to real life situations, there's a lot of algebra that is involved that makes calculus extremely difficult, okay? There's a lot of algebra in this class that makes the geometry seem to be difficult, okay? If we're taking a test, whether it be one of my tests or an course exam or something like that, you might get all the geometry right. But the only way that I judge and can judge the geometry is if you come up with the right number for X in a situation, right? And it might be the algebra that's keeping you from being able to get that X, all right? So if you're a person that knows that you struggle with the algebra in the past, my question is, what are you going to do? What are you going to do about that? Are you going to just sit on your laurels and just go with the flow, or are you going to spend time kind of revisiting that algebra, getting better at that, so it doesn't get in the way of learning the geometry? But now we're just going to substitute. So UTH was 50. HTS is 6x plus 6. And then UTS is the 13x. So I need to combine like terms. So I get 56 plus 6x is equal to 13x. 56 then is equal to 7x. X then is 8, right? Okay. Now, like if it's multiple choice, this first answer will be 8. And a lot of people will go and check that and be done, right? What were they asking? HTS. So I'm going to plug that back in. I'm going to go 6 times the 8 plus the 6. So 6 times 8, 48, plus then 6 again, 54. Now, might as well go a little bit further. If this is 54 and UTH is 50, let's plug in 8 here. What's 13 times 8? What's 10 times 8? Okay, good. So 10 times 8 is 80. 3 times 8 is 24, right? Add those together, you get 104. Does that match up to what I got as my smaller two angles? 50 and 54, I have 104, right? So once you start finding one value, two values for your problem, you might as well take the extra 15 seconds to find the third one and check yourself. Okay? Does anybody have questions on this? Do you see how it parallels, though, with what we did with segment addition? I think if you understand one of those concepts, you understand both, or you have the foundation to be able to understand both. Do you have a question? How'd you do it? Yep.
I combined them, like I subtracted the 6x from 13x to get 79. Had to bring it over to the other side, which would give me.
Right. So you're starting off. So you saw that the total. You're saying I saw the total was 13x, right? And you're going to remove then. You said the 6x plus 6, so the HTS. So you're going to remove that from this, and that should leave you with what is just left as green right here, right? Okay, so you did, and think about this. If I go back to this setup here, okay, you isolated UTH. So you're saying you took measure of angle UTH, and you let that be measure of angle UTS minus the measure of angle HTS. Isn't that the same thing as this? You just took that and put it over there on that side? Okay. So ultimately, still angle addition, you just did some of the moving of parts in a different step, a different order. But I know it looked different, but it's still the same thing. And it's perfectly fine. You can do that as much as you want. And that's fun. That works too. So you found that X was, what did we say it was? 8. So you found that to be 104 and subtracted 50 from it, and you got your 54. Perfectly fine. That works. And it'll work every time too. So good questions.